Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Welcome to section 3.4. The title of this section is Transient Response Design via Gain Adjustment. To illustrate the effect of gain adjustment on the system transient response, let us consider surveillance camera control system used in the previous video. So this is the block diagram of the system, and this is the closed loop transfer functions of the system, where K in the closed loop transfer function is actually the multiplications of the amplifier gain and also the motor gain. In this table, we can observe that as K varies from 0 to 50, the locations of the closed loop poles are varies. As K is equals to 0, which is the start point of your root locus, the system pole is located at -10 and 0. As the value of K increases, each poles change its locations until it reached 25. It has same location. At this value of K, the system is operating at critically damped response. Okay, as the value of K increases further to 30, 35, 40, 45 and 50, we can see that the poles now are complex poles. Okay, so these poles for different value of K are plotted on the figure here, on the S-plane here. So if we connect the poles, we can get the root locus. Before we proceed, let us do some revision on what we have learned in chapter 1. In chapter 1, we have learned that for a control system with underdamped response, it will has complex poles on the left hand side of S-plane as shown here. This pole is called dominant pole because it dominates the transient response of the system. So dominant pole SD is minus sigma D plus minus J omega D, where sigma D is the real value of the poles, while omega D is the imaginary value of the poles. In chapter 1, we have derived that the peak time of the transient response is equal to pi over omega d, which is the value of the imaginary part of the dominant poles, while the settling time is equals to 4 divided by sigma d, which is the real part of the dominant poles. So from this equation, we can see that the peak time and settling time of the transient response is depending on the dominant pole's location. Now, let us come back to this table. Consider for K value from 30 to 50, where the poles are complex poles, meaning that the system is operating with underdamped response. Let us calculate the settling time and the peak time of the response using the equation given in the previous slide. So when K is equal to 30, the settling time is 4 over 5, where 5 is the real part of the closed loop poles. You will get 0.8, and the peak time is pi over 2.24, which is the imaginary value of the complex pole, and you will get 1.4. Okay, for K equals to 35, the settling time is equals to 4 Still divide by 5 because the real part of the complex pole do not change as k varies. Only the imaginary parts of the pole change. So for all the k value, your settling time is maintained at 0.8, while for the peak time, you will get different value. For example, for k is equals to 35, your peak time is pi over 3.16, which is the imaginary value of the closed loop poles when k equals to 35. And as you increase the value of k, you will get bigger value of imaginary part. Thus, you will have smaller value of the peak time. And I have plot the step response for different value of k on this graph. And as you can see, the peak time for different k value is changing. And then, however, for the settling time, it is approximately around 0.8 for all the k value. In this slide, I have included another example just to illustrate to you the effect of gain adjustment on the transient response of the system. So let us consider this system. Here, this is the closed loop transfer function, and note that the system is a third order system. So if you plot the root locus, it will have 3 poles, okay? And of course it will give you 3 branch, the blue branch, the green branch, and the red branch. Okay, to evaluate the transient response of the system, it actually depends on these 2 branch only. The third branch is neglected because it is not dominant poles. Only these 2 poles are the dominant poles, which will dominate the transient response of the system. Okay, so here I have plotted the transient response or the step response of the system for different value of k. So k5, k10, k15, k20, and also k50. So if you look at the transient response part of the step response, you will see that for different value of k, you will get different TP value and different settling time value. So I hope with these 2 examples, you can see that we can actually design our transient response by varying the value of k. Using 2 examples shown in the previous slide, we have seen that by varying the system gain, you can actually change the transient response of the system. So now let us consider an example on how to design your desired transient response just by choosing the appropriate value of k. Okay, so this is a closed loop control system. So it has a 0 at minus 1.5 and it has 3 poles at 0, minus 1 and minus 10. So let us read the question. Given the system above, design the value of k to yield 1.52% overshoot and also estimate the settling time, peak time, and the steady state error. Also given the natural frequency is 5.75 radian per second. Okay, to solve the question, it involves 2 steps. The first step is you have to calculate the locations of the desired dominant poles from the given specification. So in the questions, it is given to you the desired percentage overshoot is 1.52. Using this equation, which we have used in chapter 1, you can calculate the desired damping ratio and you will get 0.8. Okay, once you have the damping ratio value, you can actually calculate the locations of dominant poles using this equation. So damping ratio is 0.8, and also given to you the omega n, which is 5.75. Substitute in this equation, you should get your desired dominant pole at minus 4.6 plus minus J 3.45. Step 2 is to calculate the K value using magnitude criterion. So this is the magnitude criterion equation which we have learned earlier in this chapter. So substitute the open loop transfer functions of the system into this part of your magnitude criterion and rearrange the equation to calculate the K value. And then substitute the value of S in this equation with your dominant poles, and you will get this equation. And then using your calculator and convert the answer to phasor form, you will get the K value equals to 39.61, and the angle is 179.9 degree. So for gain adjustment method, you have to make sure that the angle must almost equal to 180 degree or minus 180 degree, because this is to indicate that the dominant pole is on the locus, meaning that it satisfies the angle criterion. Okay. Then come back to the question. The question also asks us to evaluate the settling time, peak time, and the steady state error of the system. So since we have calculated the dominant pole, so we can calculate the settling time and also the peak time using the equation I have shown in the previous slide. So for Ts is equals to 4 over 4.6, which is the real part of your dominant poles, and you get 0.87, and peak time is pi over 3.45, which is the imaginary part of your dominant poles. You will get 0.91. And for the steady state error, since the system is a type 1 system, then you have to calculate KV using its equation, and uh, and note that I have substitute the calculated value of K from here into the KV equation, and then we will get 5.94, and the steady state error is equals to 1 over KV, and you should get a steady state error 0.17. In this slide, I have summarized the steps required to design transient response using gain adjustment. So the first step is you have to calculate the desired dominant poles location based on the specification given in the question, and using those information, you should get your ST from this equation. And then once you get your dominant poles, you have to evaluate the K value using the ST value from the step 1. And then you have to make sure that the angle must be 180 degree or minus 180 degree to show you that the SD is on the root locus. Bear in mind, gain adjustment method is only applicable if the desired dominant pole is on the root locus. Okay, I think that's all. Thank you.